So our next speaker is Josh Clune talking about Duper. Josh, are you on?
Yes, I'm here. Let me just see if I can share my screen real quick. All right.
And if you could
Um,
just go forward and back a slide real quick so we can see if the latency issue is on Zoom's
yes.
end or on
Switching slides in three, two, one, switch. Oh, wait, hold on. Sorry, that was
fake.
okay.
Okay.
Three, two, one, switch, and then three,
Yeah.
two, one, back.
Okay. There is an acceptable latency for a live presentation here.
Okay,
Okay.
great.
So you're getting started a couple of minutes late, so we're gonna cut a couple of minutes out of the coffee hour so that you get the full time allotted to you. Um, so I'm gonna sort of bump everything by 3 minutes, it turns out. Um,
All
so
right.
thanks for the flexibility. And yeah, please give a warm virtual hand clap welcome to Josh, who will be talking about Duper.
Okay. So yeah, thank you. I'm Josh. I'll be talking about Duper, a higher order proof-producing superposition theorem prover. Um, To start at the most fundamental level, duper is simply a tactic that you can call that will look at the current goal state and attempt to produce a proof that can close it. There are several tactics that do this. There's ASOP, linearith, simp, ring, search proof, and many others. The differences between these tactics lie in which goals they can close and how they approach solving those goals. Some of these tactics implement specialized decision procedures specifically for solving problems in a particular domain. Some of these tactics search through Lean's libraries for relevant lemmas to apply. Some take entirely different approaches, such as using machine learning to try and guess how a human would proceed from the current goal state. In order to use these tactics effectively, it's helpful to have an intuition for both the domain of problem for which the tactic is well suited and the basic approach the tactic employs to solve the problems, to solve problems. So for this talk, these are the two main things about Duper that I'll be trying to convey. I'll start by describing Duper's target domain. Duper is a general purpose tactic designed to close primarily first order and higher order goals. What do I mean by this? Here's Lean's overall type theory. It's a dependent type theory with inductive types and support for type classes. As we can see, Lean supports a ton of different things of varying complexities. The simplest stuff we have here belongs to propositional logic. That includes our basic logical connectives like and, or, not, and implies. If we take propositional logic and add quantification over non-logical objects, we get a many-sorted first-order logic. If on top of that, we add equality between the terms we can quantify over, we get a many-sorted first-order logic with equality. This is Duper's comfort zone. Most of the problems Duper can solve are going to be primarily first-order in nature. And from a theory perspective, the superposition calculus Duper is based on is actually complete for first-order logic, though of course in practice Duper can always just time out if a problem is too large. But first order logic isn't the totality of what Duper can operate on. If we add quantification over not just non-logical objects, but also predicates and functions, we get higher order logic. If a problem just has a few higher order features, then Duper will probably be able to handle them. But the more essential higher order reasoning is to solving a problem, the more likely Duper is to struggle with it. This is because there's some sense in which higher order logic is just fundamentally harder than first order logic. So in practice, that means that the rules Duper uses for higher order reasoning can be really expensive, making it easy for Duper to time out before it finds a proof for the goal. Although this domain of higher order logic describes the set of things that Duper can natively reason about, there are a couple more features Duper can support with some external assistance. In Yicheng's talk, in the previous talk, Yicheng was describing Lean Auto, a library that can transform some of Lean's features into first or higher order logic. Specifically, for our use case, by hooking Duper up to Lean Auto's preprocessing and monomorphization procedures, we're able to support problems with polymorphism and MATLAB style type classes by first transforming them into essentially first order or higher order problems. So everything to the right of this dotted line describes features that Duper can reason about or support to some extent, while everything to the left of this dotted line describes features that Duper isn't well suited to reasoning about. Duper won't necessarily break or crash in the presence of these features, but it also doesn't currently have the tools to effectively reason about them. Here I have some short examples of Duper in action. Both of the theorems currently on screen are lean formalizations of Smolean puzzles. On the left, I have a puzzle that can be expressed entirely in propositional logic, which we see from the total absence of quantifiers. And on the right, I have a puzzle that can be expressed in first-order logic. Both propositional and first-order logic are well within Duper's comfort zone, so neither of these puzzles are particularly troublesome for Duper. Uh, to look at some more mathematical examples, though, here I have a variety of theorems about groups. On the left, I have these theorems expressed in terms of a custom-made group type class, and on the right, I have these same theorems expressed using MATLAB's significantly more complex nested type class structure. Fortunately for our purposes, when I describe Duper as operating on first or higher order logic, I'm referring to these logics in a vague, hand-wavy sort of way, rather than giving a precise specification. Even though the example on the left is technically interacting with a group type class, all of the theorems actually being invoked are fundamentally first order, so there's no issue here. And even though the example on the right has a rather complicated type class structure under the hood, which we can see from the fact that the lemmas being passed into Duper don't even accept the same type class, this is also okay because of all the work that Lean Auto does on preprocessing and monomorphization. Each can put a lot of work to ensuring that these MATLAB style type classes can be processed and translated into problems that are fundamentally first order or higher order. So despite the type classes involved, as far as Duper is concerned, I would describe all of the theorems currently on screen as essentially first order and therefore well within Duper's comfort zone. Here I have the last slide of examples that Duper can handle without external assistance. On the left, I have theorems stating that surjectivity and injectivity are compositional, and the point of showing these theorems in particular is to show that Duper is able to handle lambda expressions without issue. And on the right, I have some theorems about summation equalities. The summations I currently have on screen are fundamentally higher order because they take in functions as inputs. So I'm showing them here to give examples of fundamentally higher order problems that Duper can solve. In addition to problems that Duper can solve on its own, there are some problems that Duper can solve with some external assistance. On the left, I have one expression of Cantor's theorem. Duper isn't quite smart enough to prove this theorem on its own, but if it's given the counterexample that shows why Cantor's theorem holds, then Duper is able to fill in the rest of the proof's details pretty easily. On the right, I have a theorem that states that if the square of a real number is equal to 1, then that number must be either 1 or -1. This problem is from a specialized domain, which isn't ideal for Duper, and indeed, if Duper tries to solve this problem all on its own, it'll fail. However, if we use the specialized ring tactic to give Duper the right helper lemma, then Duper can get the rest of the way. Neither ring nor Duper is able to close this goal entirely on their own, but together they can make pretty short work of it. Finally, I want to show two examples where Duper considerably struggles. On the left, I have a theorem that states that the absolute value of the sum of two reals is less than or equal to the sum of their absolute values. If I first case on whether these reals sum to a negative number or not, then Duper can pretty easily handle the two generated subgoals. This approach has Duper solving the first subgoal in 180 milliseconds and the second subgoal in 142 milliseconds. However, if I ask Duper to solve the entire problem all at once, it takes over 13 seconds to do it. And that's only if I make sure to both increase the number of heartbeats Duper is allowed to use and tell Duper to use the specific configuration of options that I know can solve this problem. This is a drastic difference in performance, and it can be pretty counterintuitive. An even more mystifying example of how Duper can struggle is on the right. Here, I have a simple theorem which just states that set intersection is commutative. If I apply the set extensionality lemma first, and then call Duper, there's no problem here at all. But if I tell Duper to use set extensionality itself, and all it would have to do is apply it, as we see in the top example, it'll time out even if I give Duper 10 times as many heartbeats as it would ordinarily be allowed to use. At first glance, these examples aren't significantly more difficult or complex than the ones we've seen Duper handle already. And in truth, they really aren't. So in order to understand this counterintuitive behavior, I'll need to describe a bit about how Duper actually works. Duper is something called a saturation-based theorem prover. Saturation-based theorem provers collect all of the facts they know, use some predefined inference rules to generate new facts, and then repeat this process until either the theorem prover succeeds in proving its goal, the theorem prover times out, or the theorem prover saturates, meaning it reaches a state where it can't generate any new facts. So to see kind of a bit more specifically what Duper's workflow is, yeah, let me do that. Uh, Duper will start with a goal state that has hypotheses and a target. So this is just like an ordinary lean goal state. And then the first thing Duper is going to do is it's going to collect all the facts that it has available, including the negated original target, and it'll modify the goal state so that the thing it's trying to prove is just false. It collects all the facts it knows and it attempts to derive a contradiction. And these facts that it has includes potentially things from the local context, the negated original target, as well as any lemmas that are passed into Duper. Currently, unfortunately, we do have to pass in any lemmas that we want Duper to use manually, uh, though there are plans in the future to incorporate Duper as part of like a larger sledgehammer style pipeline. And then once we have that, part of that pipeline would include premise selection, which would get rid of this annoyance. Uh, that an essential part of that pipeline would also be lean auto, um, the interface that Yicheng was describing in the previous talk. But for now, at least, we have to pass in these lemmas to Duper manually. So then after Duper has collected all of its facts and it's trying to drive a contradiction, it'll call Lean Auto's pre-processing and monomorphization procedures to turn the problem into a fundamentally first order or higher order problem. Then Duper will organize the facts that it has into a format that's conducive to its main saturation loop. Uh, it will create a passive set and an active set. The passive set is going to be a set that stores all of the unprocessed facts that Duper has. And when Duper begins, all known facts are going to be placed in the passive set. And the active set is going to be where Duper stores all of its fully processed facts. And when Duper begins, the active set is going to be empty. And I'll explain what I mean by unprocessed versus processed facts in just a little bit. Uh, After Duper has organized its facts into this format, then the first thing Duper will do is select a fact from the passive set. And we're going to call this fact the given clause. And then Duper is going to choose to focus on it. Then Duper will transform this given clause into a format that's amenable to its inference rules. This is a process that's called clausification, and I'll describe in a little bit more detail in just a couple slides. Uh, from there, Duper will use its inference rules to generate new facts from the given clause and then add them to the passive set. The Duper's inference rules require that the facts it takes as input are fully processed, and so that's why we have to classify the facts first before this state. Um, Once Duper uses its inference rules to generate as many facts as possible from the current given clause, it'll move its given clause into the active set because it's now been fully processed, and then it'll repeat the loop. And Duper will go through this saturation loop over and over again until it either succeeds, times out, or achieves saturation, which is to say that Duper's passive set is fully empty, Duper doesn't have a current given clause, and Duper isn't able to generate any more facts with its inference rules. So that's the high-level overview of Duper's workflow. I'd like to now take a moment to zoom in on the right and up arrows of this saturation loop to explain a bit more fully what I mean by processing a clause, and to give an example of one of Duper's core inference rules. There will be a lot of details that I have to leave out, but this should provide a bit more of a concrete sense of the sort of reasoning Duper is actually performing. I'll start by describing clausification. Clausification is the process of incrementally transforming facts into a normalized form. The purpose of this process is to ensure that all of our processed clauses have a standard form that our inference rules can easily work with. When a fact is fully clausified, it will be preceded by a set of universal quantifiers that quantify over the whole clause body. The clause body will be a disjunction of literals, and each literal will either be an equality between two expressions, an inequality between two expressions, or if we're dealing with propositions, a prop equated to true or false. Now that we've seen the format that Duper's inference rules require, we can look at one of Duper's core inference rules, the superposition rule. This rule takes in two fully clausified facts, at least one of which must be the current given clause, since that's the clause we're generating inferences from. The other clause will generally be taken from the active set, since that's where Duper stores its fully classified facts. The conclusion produced by this rule is wrapped in this unifier sigma. Sigma is an assignment of variables that makes E1 and U, an expression that appears in S, equal. To give an example of what I mean by that, suppose we have expressions x plus 3 and a minus b plus y, and we want sigma to be a unifier that makes them equal. In order for sigma to make these expressions the same, sigma would have to assign x the value of a minus b and y the value of 3. Then, after applying sigma, both expressions would be equal to a minus b plus 3. With that understanding, we can begin to make sense of why this rule is sound. In order for the left parent clause to be true, we either need to have E1 equals E2 be true, or something in R needs to be true. If something in R is true, then the conclusion will immediately follow because we have all of R in the conclusion's clause body. If E1 is equals E2 is true, though, then after applying sigma, E1 and U will be the same expression. So S with E2 substituted for U is the same as S with E2 substituted for E1. And if E1 and E2 are equal, then this is just the same as S. Then the conclusion will hold because we know that something in S must be true from our second parent clause. So that's the intuition behind why the superposition rule is sound, but it might not be immediately obvious how this rule could be useful in practice. To see that, let's take a look at a short example. Suppose we have these two clauses and we want to derive a new fact from them. Informally, if we undo their classification so that they can be more easily read, the left clause says that for all z of type t, r of zz implies p, and the right clause says that for all x and y of type t, either r of xy or r of yx. If we instantiate all of these quantifiers with the same free variable z, we get these clauses. Then if we eliminate the duplicated literal on the right clause, we have that R of ZZ implies P, and we have R of ZZ. Applying modus ponens to these two facts gives us that P is true, which might not have been immediately obvious from the initial two facts. So that's how we might reason about these two clauses by hand. But if we want to derive this fact using the superposition rule, how would that work? We start again with these two clauses. Then, since the superposition rule can be applied to these clauses in multiple ways, let's say that R of ZZ is E1, false is E2, and R of XY is U. Then the superposition rule gives us this conclusion. In its current state, this conclusion is a bit of an unreadable mess, so let's break it down. As a reminder, sigma is a unifier, or assignment of variables that makes E1 and U equal. E1 is R of ZZ, and U is R of XY. So to make E1 and U equal, we can assign both X and Y to have the value Z, making both expressions equal to R of ZZ. After we perform this assignment, X and Y are no longer free variables, since we assigned each of them the value Z. So their universal quantifiers disappear in the conclusion. Then we still have to apply sigma to the clause body, replacing every occurrence of X and Y with Z. And when we do, we get this. Finally, the last step is to substitute false for R of ZZ. And after we perform that substitution, the clause we obtain is this. For all Z of type T, P is equal to true, or false is equal to true, or false is equal to true. There are different rules in Duper's calculus that can eliminate the clearly false literals equating false and true. So morally, this is the same as deriving that P is true, which is what we wanted to get. So now that we've seen the high-level outline of Duper's workflow and we've gotten a sense for how Duper processes facts and generates new facts, let's return to the examples where Duper struggles to see if we can understand them a bit better. For this example, for this example on the left, Duper was able to solve the generated subgoals without much issue, but it took significantly longer to prove the whole goal in its entirety all in one go. And the reason for this is that if we look at the facts we're passing into Duper for the two generated subgoals in the top left example, we can see that the lemmas we're passing in are slightly different. Um, what this means is that when we tackle this problem in terms of two separate subgoals, we're able to, for each duper call, give duper just the facts that it needs to solve the goal. What this means is that as duper goes through its saturation loop, it's only putting a couple things in the active set. And when the active set stays small, the duper will be able to kind of on each instance of the saturation loop when it's looking at its current given clause, there are only so many things in the active set to apply its inferences to. And so that causes the saturation loop to proceed more quickly and allows Duper to operate more effectively. However, in the bottom left example, because we don't separate the goal into two subgoals, we have to pass all of these facts into Duper all at once, and which causes the active set to become significantly more bloated, which means that every time Duper selects a new given clause, and it needs to generate all of the possible inferences it can from that given clause and things in the active set, it takes a lot longer for Duper to get through that process. So the takeaway is that Duper tends to do a lot better when it's able to prove the goal with just like a small number of facts or lemmas. When the number of lemmas Duper has to deal with becomes too large, Duper can significantly slow down. There isn't like a magic number of lemmas where Duper will cut off because it depends on a lot of kind of subtle things, such as like the complexity of the lemma and the number of opportunities there are to unify in the lemma. But kind of big picture, the thing we can take away from this example is that Duper is sensitive to only receiving the facts that it actually needs to prove the goal and to receiving as few of these facts as possible. Then on the right, uh, something different is going on because in the bottom right example, we're only passing in two facts to Duper. So we don't have the same phenomenon occurring as on the left. We don't have a super bloated active set being caused by having too many lemmas or just irrelevant lemmas. Instead, what we have here is an unfortunate uh, relationship between the set extensionality lemma and Duper's core calculus. The way the Lean's set extensionality lemma is written, it's very general, and so there are lots of opportunities to unify with it in different ways. And so what this means in the context of Duper's calculus is that when Duper makes the set extensionality lemma the given clause, it'll generate tons of facts from this clause, and which will result in a super bloated passive set. If I like show you here what happens if we try to prove false and give Duper nothing except for the fact that except for the set extensionality lemma, and then I like increase the number of heartbeats so that Duper can run for a little bit, we can see that Duper will generate over 1,000 facts from just this initial set extensionality lemma. But in the process of doing so, it's only fully processing 18 facts. And so what's happening here is that each of the facts it's looking at, tons and tons of inference rules can be applied to it, generating tons of facts. And in practice, when for the previous example, all we wanted to do was apply set extensionality once and then forget about it. What's happening, what Duper is actually doing is it's spending like all of its time just trying to reason about the consequences of set extensionality. So that's an area where Duper currently struggles. So to kind of close things off, what problems can we, broadly speaking, expect Duper to solve? So as I mentioned before, Duper is well suited to primarily first order problems with some allowance for higher order features. Duper won't do as well on problems that critically involve dependent type theory. thing or features such as inductive types or subtypes. Duper does better on problems that don't require many domain-specific facts. For things like arithmetic problems, those might be better handled by domain-specific tactics. As we saw in the example with the multiple subgoals, Duper does better on problems that can be solved with a small number of lemmas. And Duper also tends to perform poorly on problems that require either lots of lemmas or really explosive lemmas, like set extensionality. And then as a final note, I'll comment that in practice, it appears that Duper tends to do pretty well on problems that can just be solved with a bunch of rewrites. And this makes sense in retrospect. This wasn't something that uh, I was expecting prior to actually developing Duper, but it's something that makes some sense in retrospect, given that the superposition inference rule, which is the primary workhorse of Duper's calculus, is essentially a really uh, general like rewrite rule ultimately. So yeah, so thanks and happy to take any questions.
Thank you very much for the talk. Before people start raising their hands to ask questions here, I'd like to deliver the first question from Zulip. Max Nowak is unable to turn on the microphone at the moment. So they wrote, is it possible to translate fin, vec, etc. into just Hall and a well-formatus predicate? Sounds like Duper doesn't do this. Oh, sorry. It says, it is possible to translate fin, vec, etc. into just Hall plus a well-formatus predicate. Sounds like Duper doesn't do this, and then in parentheses, yet. Or does it result in ugly translated problems, which are very inefficient to solve?
So uh I don't have like the specifics of how Duper interacts with those things offhand. The that component of the pipeline of taking these things that are written in dependent type theory, but they can maybe be expressed in higher order logic or in some less expressive logic, uh, doing that translation, that's a problem that Duper exports off to Lean Auto. And so that might be a better question to ask for to Yicheng on Zulip. But I do know that like Lean Auto, I mean both Lean Auto and Duper are still in active development, and so it, I mean there are three cases, right? It either can handle those things and it's fine, or it can't handle those things, or it can't handle those things yet, but maybe at some point in the future. But offhand, I don't have know enough about those specific
Yeah.
items to say. Sorry.
Oh, that makes sense. Thanks. Patrick, you're next.
Thanks, Josh. A very, very nice talk. I didn't understand the explosive lemma stuff. So in the case where you need to prove false using set extensionality, what are the lemmas that are generated in the active set? What are the facts that get into your
Yeah, it's the so I mean I can show them to you like if I share my screen, they're not going to make any sense. But I'll do that just to like appease the curiosity. I think this is the right window. Um so I think I'm sharing my VS Code's screen right now. So,
yes.
here's a bunch of nonsense that is completely unreadable. Um, the if I the set extensionality, let me show what that actually says. It has uh, it says this. It's for all A and B of like type set alpha, where alpha is like an arbitrary type. And so it's going to take a moment to generate the facts again. If I get rid of this, it'll go a little bit quicker. The like so we were yeah, it's like it's able to unify like alpha and beta with like maybe it'll be like set of alpha, or then set of alpha, or it'll do other things. The like here we see that for some reason Duper is thinking about set of alpha. And the point is that the like Duper's inference rules, they're designed to be like, as complete as possible. But what that means is that when you have like this really general fact like set extensionality, you can get all sorts of things from that. So uh, something that I'm currently working on is trying to like add some better heuristics to try to curtail this behavior where Duper spends a bunch of time reasoning in the totally wrong direction. But it's a difficult problem for superposition theorem provers in general, and so it's just a difficulty of the approach.
Okay, thanks.
Thank you very much, Josh, for a great talk.